everybody. Today we're going to be learning about section 6.6, which is on nuclear energy. The learning objective for today is that you can describe the use of nuclear energy in power generation and that you can describe the effects of the use of nuclear energy on the environment. You're going to learn some essential knowledge about how nuclear power is generated, the uranium molecules that are involved in that, and some of the past incidents with nuclear power plants. And yeah, just kind of some basics about this process. So first of all, we're going to talk about the process of nuclear fission and radioactivity and kind of how this is just kind of like the basics of this. So the process for generating electricity through nuclear power is going to be very similar to what we see with fossil fuels, where essentially you are creating heat that's going to steam, which is going to cause a turbine to move, etc. Except instead of combustion of fossil fuels, with this one, we're using nuclear fission. And this is going to be when you have a neutron fired into the nucleus of a radioactive element. Radioactive means it's unstable, such as uranium. Uranium is going to be the main one that we use in this process. So what happens is the nucleus is going to break apart and it releases a bunch of energy, which is heat. However, in addition to this initial reaction that releases heat, you're also going to have more of the neutrons just going and breaking apart. And you have then more nuclei apart, and then it just kind of causes this chain reaction of more and more and more energy being released. And so if you look at this right here, we're going to start with one of them, which is going to cause more of these neutrons to go, which is going to cause a chain reaction, which is going to have more of this fragmentation. And again, it's a chain reaction that results in a lot of heat. Now, some terminology that you should be aware of with this conversation. First of all, what is radioactivity? This is going to refer to the energy that's given off by the unstable nucleus of a radioactive isotope. So specifically, the radioactive isotope that we're looking at is going to be uranium-235. And what happens is you have this radioactive decaying of the nuclei, or the breakdown of the nuclei, and this gives off energy. It gives off the radiation, even without fission. So like in a normal process where you aren't having this whole like chain reaction fission process, some radioactivity is normal. You're going to have uranium giving off some basic radiation, but it's the nuclear fission process that's going to release tons of it all at once. Now, one of the terms that you also should be aware of is what's known as radioactive half-life. And this is going to be the amount of time that it takes for 50% of a radioactive substance to decay, to break down. So, for example, if we're going to look at cobalt, the half-life of a cobalt-60 isotope is about 5.27 years, which means that in 5.27 years, half of a cobalt-60 sample would be gone. It would be decayed. So if we look at this graph here, for example, if we start with 10 grams of this cobalt-60 isotope, after 5.27 years, so after one half-life, we would then have 5 grams. After another half-life, it'd be 2.5. After another half-life, it'd be 1.25, etc. So you're having over this time. Now, the half-life of a isotope, it varies. Like cobalt is going to be different than uranium, but scientists do know the half-life of these things because they've done a lot of research into finding it. But that's what it means by the radioactive half-life, is going to be the amount of time that it takes for that breakdown. So now, how do we generate electricity? As I said, it's basically going to be the same process as with fossil fuels. We're just using uranium fission to heat the water into steam. So we've got the heat from this really powerful energy releasing reaction That heat is going to turn water into steam. That steam is going to turn a turbine. That turbine is going to power a generator, and the generator is going to produce electricity that can go out into the power grid. So the way that we generate electricity, we have this uranium-235 that is stored in these fuel rods. And you take these fuel rods and you submerge them into water in this like reaction core area. And this is where you're going to get the heat from the fission turning the water into steam. So for example, this is going to be like what a nuclear power plant generally is going to look like. You're going to have water that's going to be coming in to this like core reaction core area. Now we've got these rods that you then go and put into the water. Now, when these rods go into the water, these fuel rods get super hot because they have this nuclear fission occurring. And so that's going to heat up the water, which is going to release steam, which, as you see, then goes into the turbine, to the generator, to the transmission line. Now, what's kind of cool is in a nuclear reactor, you're going to have some of this like water vapor being created, which then when it cools down, it can be collected, and that water can then be recycled to like keep going back into the core so that you can kind of keep reusing some of that water. Because again, it's then just going to be steam, which then, yeah, that process kind of keeps going there. Now, so these control rods are lowered into, the control rods are going to be a safety mechanism because there's a ton of heat that's being released in this, and we're dealing with radioactive material. So you need to have some safety mechanisms. So one of them is going to be the control rod. So you put the fuel rods in the water, they're submerged in there. And then these control rods are going to be ones that when you have the reaction going, you can have the control rods go down, and they can absorb extra neutrons to slow down the reaction, which is going to prevent a meltdown or like an explosion. So not only do we have the fuel rods that are in there, we also have the control rods that can be used as a safety mechanism. We also, as a safety mechanism, are going to have a water pump, which you can see right here on our diagram. What this does is it brings in cool water to be turned into steam, but you can also pump more of that cool water in to keep the reactor from overheating. So we've got the control rods and we've got the water coming in through the water pump. Additionally, we have a cooling tower, which is this big. If you have ever seen a nuclear reactor, the big like stack that goes up, that's the cooling tower. And what this allows is it allows the steam from the turbine to condense back into liquid and cool down before being reused, which gives off that water vapor. You have some of it that goes out the top of the tower, but you have some of it that's going to condense that can then go to continue being used for cooler water for the water pump safety mechanism. Now, nuclear energy is considered a non-renewable source, but it is much cleaner than fossil fuels. So the reason that nuclear energy is non-renewable is because radioactive elements like uranium are limited. We only have a certain amount of uranium here on planet Earth, and so it is not a renewable resource. However, when you go through this nuclear process, it does not release any air pollutants or carbon dioxide or methane when electricity is being generated. So that is kind of an important distinction. The actual process we just talked about with like the turbine and the generator doesn't release air pollutants or the carbon dioxide or methane. However, the process of mining the uranium and constructing these power plants does release those greenhouse gases. But like once it's there, outside of the mining, the actual electricity process is not going to be releasing those. The only gas that is released from this process is water vapor. Now, water vapor technically is a greenhouse gas because it can absorb heat, But it stays in the atmosphere very briefly. It's going to cycle. The amount of water vapor that's being held in the atmosphere is based on the local temperatures. So it's technically a greenhouse gas, but we definitely don't consider it as serious as the carbon dioxide or the methane that we're typically concerned about with these fuel methods of hitting fuel. Now, the other big main drawback of nuclear energy is going to be the possibility of meltdown and radioactive contamination. Radioactive contamination is basically the biggest downside of nuclear energy. So one of the radioactive contamination concerns is going to be spent fuel rods. So the fuel rods that are in there where you're having all this uranium and the fission occurring, those things, even when we're done using them, they remain radioactive for millions of years. And they need to be stored in lead containers, usually on site at the power plant. So spent fuel rods get stored like this, radioactive material. They are then often put into these big, lead things, but eventually the lead things can break down. You've got to constantly be making sure that they're not getting released because, again, these fuel rods are going to be radioactive for basically ever, for millions of years. So that's going to be a concern of that potential contamination. Another concern is going to be the mine tailings. So when we are mining that radioactive material, like we talked about with mining, you end up having leftover rock and soil and water that's going to be contaminated that then is stored usually in these tailing ponds, which can flood and then contaminate local water or soil. And then additionally, water use is going to be a drawback. Nuclear power plants require a lot of water, and so they can deplete local surface or groundwater sources. And then we also have thermal pollution. The water in the power plant, there is hot water that is released back into surface waters, and that can cause thermal shock. So if you look at this thermal imaging of a power plant and the water that is released, it's way hotter than the water around it. So when this is released into surface waters, this can lead to decreased oxygen and suffocation and changes in the temperature range for the organisms that are living there in that surface water. Now, nuclear meltdowns, which are kind of like the big part that everyone is afraid of. And there's going to be three of the most famous ones, and these are the three for the AP test that you need to know about, but just generally, they're also the most famous ones. So we've got the 3 Mile Island, which happened in the United States, Fukushima, which happened in Japan, and then Chernobyl, which happened in Ukraine. So 3 Mile Island happened in the United States in 1979. It was a partial meltdown due to a testing error. Radiation was released, but there were no deaths, and scientists have done longitudinal studies and have not found any cancer cases related to it. But the reason it's important is because this event basically terrified the US population about the potential for using nuclear power and nuclear meltdowns. And so since then, no reactors have been built in the United States since. Actually, in the 70s, there was a huge push for nuclear. We were having tons of them being built, and 3 Mile Island happened and it stopped production. So if 3 Mile Island hadn't happened, nuclear power might be way more widespread here in the United States. The next one is going to be Fukushima, which happened in Japan in 2011. Now, what happened here was a major earthquake and tsunami. And the tsunami, when it hit this power plant, it triggered the cooling pump feature. So if you remember, the cooling pump is what puts in cool water to keep the temperatures lower. So that failed, which meant that the water and everything in this chamber got super duper hot, which just led to a meltdown. The core reactor exploded, and there was widespread radiation release, it even went into the oceans, and scientists are still studying the effects of that because it actually happened somewhat recently. And then the last one, which you probably have heard of because it's like the most famous one, is going to be the Chernobyl meltdown that happened in Ukraine in 1986. What happened was that cooling valve got stuck, which led to a complete meltdown. Like the reactor exploded. There were several deaths and widespread radiation release. So if we look at this like image here, remember the water pump is going to go and be putting that cool water in so that the reactor, like you're leaving the steam, but you're continuing to have cold water pumped in there to keep the temperatures lower. This failed, which means this just got super duper hot. The water boiled over, fuel rods got overheated, and explosion. Now, the environmental concerns of these meltdowns is, first of all, radiation causes cancer and genetic mutations in people, animals, and plants. So it's like scary, dangerous. We ended up with contaminated soil. Radiation can remain in the soil and harm plants and animals in the future. Radiation also, like kind of the big scary part, is that it can be carried by the wind over long distances, which will affect, it's not just the meltdown site that gets affected, it can be spread far. So if we look here, Chernobyl happened in Ukraine right here, but you can see increased radiation across all of Europe. So even those like hundreds of miles from Chernobyl, there were people who still were having like slightly elevated radiation levels, which is obviously scary that it can spread that far. So we're not just talking about like, we'll put it in an isolated area, and if something goes wrong, we're fine, because it can spread through the wind. So this is going to be your practice FRQ for 6.6, where you're going to be using visual representations to explain environmental concepts. So looking at this diagram here, I want you to identify and describe one letter in the diagram that is common to both nuclear and fossil fuel electricity production. And then I want you to identify and describe one letter in the diagram that is found only in nuclear power plants. So we've got letter A right here, B, C, and D. So that will be your practice FRQ for 6.6, and those were your notes on 6.6 about nuclear power.